have been learning about different types of deviations and how these can be used to better understand the relationship of a response and explanatory variable, as well as to help us understand the characteristics of individual units when we model that relationship. In this video, I want to continue looking at using deviation scores to statistically analyze data when we are exploring a relationship. Specifically, I'm going to talk about sums of squares. Sums of squares is short for sums of squared deviations, so this continues our exploration of deviation scores. There are three types of deviations: total deviation from the mean, the portion of this deviation that we can understand with a linear model, and the remaining deviation that is unaccounted for by the model, so which can be understood as the error of the model. The total deviation can be partitioned into two parts so that the sum of the model deviation and error deviation equals the total deviation. This partitioning helps us explore what part of the total deviation is explained by the model and what part is not explained by the model. If we were to add up all the deviations from the mean, this would equal 0, because positive deviations and negative deviations cancel each other. The way we handled this when defining the standard deviation was to square the deviations before adding them, thus eliminating the negative values so that we can sum a set of positive numbers. We can use the same trick when we want to sum any type of deviation scores. When we square deviations and add them up, this is referred to as a sum of squares. We have defined three types of deviations, so there are three types of sums of squares. The total sum of squares is the sum of squared deviations about the mean. The model sum of squares is the sum of the squared model deviations. The error or residual sum of squares is the sum of the squared deviations from the regression line. Just as the model deviation plus the residual deviation equals the total deviation, the model sum of squares plus the residual sum of squares equals the total sum of squares. The total sum of squares can be partitioned, just as we can partition total deviation. Let's look at an example of calculating the sums of squares and see how we can use these to better understand the relationship of a response and explanatory variable. For this example, we are going to model the power of an engine as a function of engine size. That is, we are going to look at how horsepower changes when the displacement of the engine changes. If you watched the previous video, you have already seen the first part of this script. I'm going to load the data, then pull out the displacement and horsepower variables. The total deviation from the mean of our response variable, horsepower, is calculated by subtracting the mean horsepower from the horsepower for each of the individual units. Now let's calculate the total sum of squares. To do this, we need to square each deviation and then add them all up. I'm going to store the result in a variable that I have named ss.total. To calculate the other types of deviations, we need to create a linear model. I'm going to do that. Then I'm going to pull out the predicted and residual values from that model. The model deviation is calculated by subtracting the mean horsepower for the set of automobiles from the predicted horsepower for each automobile. To calculate the model sum of squares, we square each of the model deviations and then sum these squared model deviations. Residual deviations have already been calculated for us, so to calculate the residual sum of squares, we square the residual deviations and then sum the squares. Now, if we've done this correctly, the total sum of squares should equal the value that we get if we add the sum of squares for the model and the sum of squares residual. Here's the total sum of squares. Now let's add the sum of squares for the model and sum of squares residual. Good news! They match. Now it is time to see how these sums of squares can help us understand the strength of our linear model. I know that the total sum of squared deviations from the mean can be partitioned into the sum of squares that is accounted for by the model and the sum of squares that is not explained by the model. What I want to know is what proportion of the total sum of squares is accounted for by the model. To determine this, I simply look at the ratio of model sum of squares to total sum of squares. That is about 0.63. When we model horsepower from engine displacement, we know that 63% of the variability in horsepower among the automobiles can be explained by or attributed to engine displacement. Similarly, if we take the ratio of the sum of squares residual to the sum of squares total, we will see what proportion of the variation in automobile horsepower is not explained by engine size, but must be due to factors that are not in our model. We find that 0.37 or 37% of the variation in horsepower cannot be explained by the variation in engine size. Since the total sum of squares can be partitioned into model and residual sums of squares, if we add up the proportion of variation that is explained by the model to the proportion of variation that is not explained by the model, this will equal 1. That is, 100% of the total deviation is either explained or not explained. We began our study of the variation of horsepower in automobiles by picturing and describing that horsepower with graphs and statistics. We then studied whether some of that variation can be explained by the variation in engine size. This led us to a linear model in which we viewed horsepower as a function of engine displacement. Now we can assess the strength of that model. We know that we can explain a sizable portion of the variation in horsepower, 63%, with the size of the engine. We also know that even after accounting for engine size, some variation remains. We are not explaining 37% of the variation in horsepower. So if we want to understand that variation, we will need to look at additional factors that might account for different automobiles having different horsepower. The study of the relationship among two quantitative variables consists of these two parts: modeling a response variable as a function of an explanatory variable, identifying the components of that model that will inform our understanding of this relationship, and assessing the strength of the model. In the next video, I will bring these two analytic pieces together to illustrate how these parts complement one another to provide a substantial understanding about the relationship among two quantitative variables.